Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Cosmic Pioneers. How robots are revolutionizing space exploration. The role of robots in space exploration has been transformative, enabling humanity to reach further into the cosmos than ever before. From the early days of space exploration to the cutting-edge missions of today, robotic spacecraft have been at the forefront of our quest to understand the universe. This narrative delves into the history, achievements, and future prospects of robotic space exploration, highlighting how these mechanical pioneers have expanded our horizons and enhanced our knowledge of space. The journey of robotic space exploration began in the mid-20th century, during the height of the Cold War. The Soviet Union launched the first artificial satellite, Sputnik 1, on October 4, 1957. This historic event marked the dawn of the space age and demonstrated the potential of robotic spacecraft. Sputnik 1's success spurred the United States to accelerate its own space program, leading to the creation of NASA and the beginning of the space race. One of the earliest milestones in robotic space exploration was the launch of Luna 2 by the Soviet Union in 1959. Luna 2 became the first human-made object to reach the Moon, providing valuable data about the lunar surface. This was followed by Luna 3, which captured the first images of the far side of the Moon, a region never before seen by humans. These early missions demonstrated the capabilities of robotic probes to conduct scientific investigations and relay data back to Earth. The United States soon followed with its own robotic missions. The Mariner program, initiated in the 1960s, aimed to explore the inner planets of the solar system. Mariner 2 became the first successful mission to another planet when it flew by Venus in 1962, providing the first close-up measurements of another planet's atmosphere and surface conditions. Mariner 4, launched in 1964, achieved another milestone by performing the first successful flyby of Mars, sending back the first images of the Martian surface. These early robotic missions laid the groundwork for more ambitious endeavors. The Viking program, launched by NASA in the 1970s, aimed to explore Mars in greater detail. Viking 1 and Viking 2 both consisted of an orbiter and a lander, making them the first missions to successfully land on Mars and conduct long-term scientific studies. The Viking landers performed a variety of experiments, including searching for signs of life, analyzing the Martian soil and atmosphere, and capturing panoramic images of the Martian landscape. The data collected by the Viking missions provided a wealth of information about Mars and its potential to support life. Robotic missions continued to push the boundaries of space exploration in the 1970s with the Voyager program. Voyager 1 and Voyager 2 were launched in 1977 with the primary mission of exploring the outer planets of the solar system. Both spacecraft performed flybys of Jupiter and Saturn, sending back detailed images and data that revealed the complex and dynamic nature of these gas giants. Voyager 2 continued its journey to Uranus and Neptune, providing humanity with its first close-up views of these distant planets. The Voyager missions have since entered interstellar space, continuing to send back data from beyond the solar system, making them some of the most successful and enduring robotic missions in history. The 1980s and 1990s saw significant advancements in robotic space exploration, particularly with the advent of robotic rovers. The Soviet Union's Lunokhod program, which included the first successful robotic rover missions to the Moon in the 1970s, demonstrated the potential of mobile robots to explore planetary surfaces. Building on this success, NASA developed the Mars Pathfinder mission, which included the Sojourner rover. Launched in 1996, Mars Pathfinder and Sojourner demonstrated the feasibility of deploying rovers on Mars, providing valuable data about the Martian surface and paving the way for future rover missions. The success of Mars Pathfinder led to the development of more sophisticated rovers, including Spirit and Opportunity, part of NASA's Mars Exploration Rover program. Launched in 2003, these twin rovers were designed to explore different regions of Mars and search for evidence of past water activity. Both rovers exceeded their expected lifespans, with Opportunity operating for nearly 15 years. Their discoveries, including the identification of ancient water-altered minerals and signs of past habitable environments, have significantly advanced our understanding of Mars' geological history and its potential to support life. Another groundbreaking robotic mission was the Cassini-Huygens mission to Saturn, launched in 1997. Cassini, a joint endeavor between NASA, the European Space Agency, ESA, and the Italian Space Agency, ASI, was designed to study Saturn and its complex system of rings and moons. Cassini's detailed observations revealed the dynamic nature of Saturn's atmosphere, the intricate structure of its rings, and the diverse characteristics of its moons. One of the mission's most significant achievements was the deployment of the Huygens probe, which landed on Titan, Saturn's largest moon, in 2005. Huygens provided the first direct observations of Titan's surface and atmosphere, revealing lakes of liquid methane and complex organic chemistry. Robotic exploration has not been limited to planetary missions. The study of comets and asteroids has also been a focus of robotic space missions. One notable example is the Rosetta mission, launched by ESA in 2004. Rosetta was designed to orbit and study the comet 67P/Churyumov-Gerasimenko. After a decade-long journey, Rosetta successfully rendezvoused with the comet in 2014 and deployed the Philae lander. Although Philae's landing did not go as planned, it managed to transmit valuable data about the comet's composition and structure. Rosetta's observations have provided critical insights into the origins and evolution of comets and their role in the solar system. In recent years, robotic missions have continued to push the boundaries of space exploration. The Curiosity rover, part of NASA's Mars Science Laboratory mission, was launched in 2011 and has been exploring Mars since its landing in 2012. Curiosity's sophisticated suite of instruments has allowed it to conduct detailed analyses of Martian rocks and soil, revealing evidence of past habitable environments and the presence of organic molecules. Curiosity's findings have deepened our understanding of Mars' potential to support life and have informed the planning of future human missions to the Red Planet. The exploration of asteroids has also advanced with missions such as NASA's OSIRIS-RX and Japan's Hayabusa 2. OSIRIS-RX, launched in 2016, successfully rendezvoused with the asteroid Bennu in 2018. The mission aims to return a sample of Bennu's surface material to Earth, providing valuable insights into the early solar system and the building blocks of life. Similarly, Hayabusa 2, launched by JAXA in 2014, successfully collected samples from the asteroid Ryugu and returned them to Earth in 2020. These missions have demonstrated the feasibility of sample return missions and have provided critical data about the composition and history of asteroids. Looking to the future, the role of robots in space exploration is set to expand even further. The Mars 2020 mission, which includes the Perseverance rover, is searching for signs of past life. Perseverance is equipped with advanced instruments and technologies, including a helicopter drone named Ingenuity, which demonstrated the feasibility of powered flight on another planet. In addition to Mars, robotic missions are being planned for the exploration of other moons and planets in our solar system. NASA's Europa Clipper mission, set to launch in the 2020s, will study Jupiter's moon Europa, which is believed to have a subsurface ocean that could potentially harbor life. Similarly, ESA's JUICE, Jupiter Icy Moons Explorer, mission will explore Jupiter's moons Ganymede, Callisto, and Europa, providing detailed observations of these intriguing worlds. Robotic spacecraft are also being developed to explore the outer solar system and beyond. NASA's Dragonfly mission, scheduled to launch in 2027, will send a rotorcraft to Saturn's moon Titan to study its surface and atmosphere in unprecedented detail. Additionally, the proposed Interstellar Probe mission aims to travel beyond the heliosphere and study the interstellar medium, providing valuable data about the environment between stars. The advancements in robotic space exploration are not limited to planetary missions. Robotic spacecraft are also being used to study the Sun and its impact on the solar system. NASA's Parker Solar Probe, launched in 2018, is designed to study the Sun's outer atmosphere and solar wind. The probe's close approach to the Sun has provided valuable data about the mechanisms driving solar activity and its influence on space weather. Furthermore, the role of robots in space exploration extends to supporting human missions. Robotic systems are being developed to assist astronauts on the International Space Station, ISS, and future lunar and Martian habitats. Robotic arms, drones, and autonomous rovers can perform tasks such as maintenance, repairs, and scientific investigations, reducing the workload on astronauts and enhancing the safety and efficiency of human missions. One of the most ambitious future goals for robotic space exploration is the establishment of a sustainable human presence on the Moon and Mars. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, with the long-term goal of establishing a lunar base. Robotic landers and rovers will play a crucial role in scouting landing sites, conducting scientific investigations, and demonstrating technologies needed for sustained human presence. Similarly, the goal of sending humans to Mars relies heavily on robotic exploration. Robotic missions to Mars are providing critical data about the planet's environment, resources, and potential hazards. This information is essential for planning safe and successful human missions. Robotic systems will also play a key role in supporting human activities on Mars, including habitat construction, resource extraction, and scientific research. The role of robots in space exploration is not limited to governmental space agencies. Private companies are increasingly becoming involved in robotic space missions. Companies like SpaceX, Blue Origin, and Astrobotic are developing robotic spacecraft for a variety of purposes, from lunar landers to asteroid mining. SpaceX's Starship, for instance, aims to transport both cargo and humans to Mars, while Astrobotic's Peregrine lander is set to deliver scientific payloads to the Moon. The involvement of private industry is accelerating innovation and reducing costs, making space exploration more accessible and expanding its scope. In conclusion, the role of robots in space exploration has been and continues to be transformative. From the first satellites and lunar probes to the sophisticated rovers and interstellar missions of today, robotic spacecraft have vastly expanded our knowledge of the cosmos. They have explored distant planets, moons, and asteroids, revealed the mysteries of our solar system, and even ventured into interstellar space. As technology advances, the capabilities of robotic explorers will only grow, enabling humanity to reach new frontiers and uncover deeper secrets of the universe. The synergy between robotic and human exploration promises a future where we can push the boundaries of what is possible, exploring the vast expanse of space with ever greater ambition and precision.